Everybody, thank you for joining us today. My name is Jim Walker. I wanted to welcome you to today's edition of the Cockroach Hour. Today we have another special guest. We've had somebody from Red Hat before. Actually, twice now I've been on webinars, but I'm really excited today for this. As always, I get real excited when our topic is Kubernetes, and that's going to be a heavy load today and a heavy lift on what we're going to talk about. So today we're going to talk about geographically distributed database with OpenShift, and I have two guests. But before we get started, real quick, a little bit of housekeeping. Of course, yes, absolutely. A recording will be available of this session after the event. So if you want to share with anybody or review anything that the guests have gone through, please by all means do. I think we are actually streaming to YouTube today as well. I think this is the first time we're doing that. I think we've done it for a couple other little things, but we're doing that now. So it'll be on our YouTube channel. You'll always find everything that we do there. There's a growing list of great material there. But during the session, I've got two guests, and they can answer all types of different things. And I've got a team of people in the background who are happy to ask really any questions that come up. Please do ask questions in the QA panel in Zoom. It'd be great if you're on that channel. If you're on YouTube, then I'm not sure if we're monitoring that. I think it's just in the Zoom side. And then please engage us in chat. For some of the best questions, as we always do, we like to give away some swag. We have these beautiful water bottles. I don't have one with me, but it's actually, these are collector editions because this is our old logo. You see, we changed logos here. So get your collector edition water bottle by asking lots of questions, and please do be engaged. So with that, I am going to ask our panelists to come on video. Raphael and Keith, if you could join me, that's great. Today's session, we typically get asked, what level is this session? I would say this is kind of intermediate to advanced. This isn't the life of a transaction, Keith, but it's definitely some advanced stuff in the Kubernetes side of the world, right? We're talking about, multi-cluster and networking and these sort of things. So we're gonna do some pretty deep topics here, but I think there's some lessons to be learned just about distributed systems and some of the challenges that we all face as we deploy, even just simple applications across, across compute. Lots of stuff that we're going to talk about today that there should be some pretty good takeaways. So definitely not basic, definitely intermediate to advanced today. So I'm real excited. Again, anytime we talk about Kubernetes, I'm usually joined by what is your title now, Keith? I want to introduce Keith McClellan to everybody. Say hi, Keith.
Hi, but before I introduce myself, that doesn't look like a Zoom background. Are you in an office, Jim?
Yes, I am. Yes, thank you. Actually, so any of my fellow Roachers who are on the call today, and if you joined in the last year, this is actually what our office looks like. Anybody who's on the call who hasn't been in an office, your office might look like this. It's plastic. I've never done a webinar from a desk, so I had to be in New York. I live in Denver. I had to be in New York, and I needed space because I couldn't work out of the place where I was. So that's why I'm here. This is not a fake background. It's not a train station like you, Keith. But thanks for
coming. Keith McClellan, solutions engineer here at Cockroach Labs. I am kind of the Kubernetes subject matter expert. I've been working a lot on our operator project and lots of other great things related to kind of cloud native computing and how CockroachDB can kind of help make that a reality for our customers. So thanks for having me today, Jim.
You bet, Keith. And y'all, like Keith has extensive experience in Kubernetes and just orchestration in general. Your background is peppered with some really interesting companies and interesting projects. And the work that you're doing on our operator is it's awesome. And so if you all want to be involved, talk to Keith.
And most importantly, I wore a red shirt in honor of our guest from Red Hat. Wow. I don't have a red hat. They haven't sent me a red fedora yet, but I'm still inching to get one at some point this year.
Well, thanks for that, Keith. And I want to introduce Raphael Spazzoli as well. So Raphael, can you just give us a little bit about yourself and what your role is at Red Hat?
Yeah, hi. Good morning or afternoon to everyone. Yeah, my name is Raphael Spazzoli. I am an OpenShift architect in Red Hat Consulting Services. I have been with OpenShift essentially since the beginning of the OpenShift journey and helping customers install, deploy, and adopt OpenShift and deploy applications on it.
That means that the demo is how you would actually want to do it and not how I would build it. So we're going to get to see like a production candidate architecture as our demo today. It's really exciting.
So what we have like a pro and a hack, and then a double hack on me. So
I'm definitely the hack. I'm 100% the hack for sure.
Double hack over here. So Raphael, really seriously, welcome to the session, and thanks for joining us and taking the time today. And you guys, to the audience, the demo that we're going to go through today is pretty phenomenal, as Keith said. I mean, this is kind of some production grade stuff that we're going to talk through. Raphael, you do work with a lot of my my ex counterparts. I was at a little company called CoreOS that became part of, and we built Tectonic, right? And so I know that group became part of the OpenShift team. So it's good to meet, I guess, my old peers, new peers is what this is. So, well, great. So let's just start here then, you guys. I'm going to stop sharing so that it's us on screen. So, let's just before we jump into the deep tech demo side of things, guys, what we're going to talk about today is kind of multi-cluster and some of the challenges that organizations have as they try to do these. I mean, I think in even single cluster, there's a lot of challenges that people face, definitely around, I always think of security, networking, and storage as kind of the big three areas that people do struggle with. And, Keith, we spent a lot of time thinking about the database here, but Raphael, you're in talking to a lot of customers, you're talking production experience with OpenShift. I mean, OpenShift is everywhere. It's, in our customer base for sure, we're just so proud to partner with y'all because you're pushing the bounds of kind of what Kubernetes can do and really kind of simplifying and make it easy. That, okay, I'm not going to give the Redhat OpenShift pitch, but you're seeing data. When I started in this whole game, the whole Tectonic thing at CoreOS, it was like, well, yeah, stateless workloads, it was great, but stateful stuff was a little bit difficult, right? This is before Clayton had actually built out stateful sets and whatnot, right? So, how much are people trying to deploy databases today, either on Kubernetes or kind of next to it? And is this kind of a core part or core challenge that people are having?
Yes, thanks for the question. Yeah, I can confirm that we have essentially solved the stateless, problem as in terms of deploying stateless workload on Kubernetes. And when I say we, a few years ago, I might have meant the Kubernetes community, but now I really mean all of the Kubernetes users. Like everybody understands how to do that, and now there is a growing interest on stateful, because the reality is that applications have not changed and they have a state somewhere, whether it's in a cache or in a queue or in a database or NoSQL database, but state is always somewhere. So now there is interest in starting to take those workloads and making more cloudify those workloads. And in a lot of times, I don't want to say always, but a lot of times, I mean running them in Kubernetes.
Yeah.
So to answer your question more directly, all of the customers that I see, which is obviously a limited spec, but all of the customers that I see are considering that, or actually doing that.
Yeah. Well, and I think that's why this partnership to me is so exciting, because it's kind of like, do you use the right database for the right problem? What's the right database for a distributed environment? For me, when I first saw CockroachDB, Spencer, our CEO, it was about 4.5 years ago, I think. It was at an OpenStack Summit. With those old shows, if anybody remembers those, they used to be a big deal. I think KubeCon has kind of blown that out of the water lately, but they were showing, Alex Bolvey, who was the CEO of CoreOS, was up there showing killing pods with Cockroach running on. The database was not really having any impact, right? And it was awesome. But I think what it showed is, like, I think there's key primitives of distributed systems, one of them being scale, the other being resilience. And, Keith, you and I have had some conversations about this. And just earlier today, you were talking about how clusters should be considered kind of to be fault tolerant as well. How are people thinking about it in your mind?
Yeah, so the Kubernetes cluster is the new failure domain, right? So
interesting.
So if you're talking about like legacy data center setup, right, you're really handling kind of two types of failure domains: racks, right? You want to manage for a rack failure, not just a server failure, but a rack failure. And then you want to manage for a site failure. So in traditional asynchronous HA is designed for organizations that have two sites, one that's primary, one that's their backup. We're going to get into this a whole lot, as we go through the chat, right? As we move to the cloud, we realize that the cloud environment, like whatever region or availability zone we're running in, that's our new fault domain, right?
Right.
So we still have to manage for node failures, but we've been managing for node failures for a long time. But rather than managing for rack failures and data center failures, now we're managing for availability zone and region failures. And because Kubernetes has effectively become the de facto, I'll call it operating system for the cloud, right? At least for cloud native applications. The new fault domain is effectively the Kubernetes cluster. And how do we manage a workload that continues to survive even if that all of that infrastructure goes away? And I don't want to steal Raphael's thunder, but like that's I will. That's what I will. That's what we're going to be showing today is treating an entire Kubernetes cluster like it's some resources that might just fail and might go away on us unexpectedly, and wanting to make sure that our workload and our applications can continue to work. So It's a lot of our customers want to do this in production. And anyone that's tried this knows that it's not easy. So the fact that we've got a nice kind of, well thought out architecture where we can solve this problem for customers is a win in my book.
Yeah, networking is no joke. Networking within a single network is no joke, let alone, or understanding it at least. I mean, way back in my undergrad days, I was networking. That was my CS undergrad focus. So I don't understand it. I don't understand this anymore. And then doing it across multiple different networks. Go on, Keith, sorry.
No, so networking is just one of the components that we solve. So we got into this specifically because of the networking problem, but the solution that Raphael and I kind of built together solves for more than just that. And we're going to get into how we're kind of solving for like distributed trust as well, right? So that's at least a part of the security element. How we're managing distributed state, that's what CockroachDB is doing as a part of this architecture. And then, as you mentioned aptly, we're using Submariner as the kind of the distributed network environment that's helping us kind of bridge the gap between these three environments.
Yeah, they're all significant. It's all significant challenges. Early days of Kubernetes, there was a special interest group, a SIG around federation, and man, it had its fits and starts because there were like 15 problems to solve, right? And so I think what we're going to show here today, and let's get into it, guys. Let's just go right into the stuff. Is some of the issues that I think need to be solved as we go forward and start thinking about a cluster as a failure domain, which I think is actually a really interesting way to think about this stuff. So Keith, do you want to show the presentation, or do you want me to actually show the slides?
Yeah, I can do it. Hold on a sec.
Okay, yeah. There's a few slides. They're all technical in nature, and we'll go through a little bit of the architecture that the demo's gonna outline. But
we're gonna do. Awesome. See my screen?
Yep, you bet.
All right.
And then remember, everybody, please do ask questions, QA and chat. Tim and Jim from our team, Tim and Jim, I guess we'll be monitoring and funneling some questions into Keith or Raphael along the way. So thank you.
Yeah. So Raphael, let's kind of start this conversation around how people used to do this, right? So can you kind of walk us through what you've seen your customers try to do and probably fail at over and over again with traditional DR?
Yeah. This is a thought that I started considering about 2 years ago when, like I said, like we mentioned, the stateless problem was solved, and I started focusing more on stateful. There is a lot to consider with stateful. There is storage. There is how you do backups, there is how you do maintenance. But the thing that attracted my attention mostly was how do we survive failures, right? And so availability, but not just availability, but disaster availability when there is a disaster, which normally I think we all map to the loss of a data center, but with cloud, that could be the loss of a availability zone or of a region, or like Keith was saying now, Kubernetes is the failure domain, so we could map it to the loss of a Kubernetes cluster. So I started trying to paint the picture of what cloud native disaster recovery might look like, and if trying to differentiate it from the traditional disaster recovery. And this is the summary that I would like to present to you, so that we can talk about disaster recovery, cloud native disaster recovery as a new concept. So normally in traditional disaster recovery, this is not necessarily with containers, right? This is what happens even when you have VMs. There is a human decision to recognize or acknowledge that there is a disaster and trigger the DR procedure. So that involves somebody realizing that there is a problem and then determining that the problem is so bad that we have to call it a disaster and start the disaster recovery procedure. It's not fast, right? In cloud native, we want it to be the system that makes the decision and autonomously detect the situation and reacts to it. And then once we decide that we have a disaster, what is the procedure, right? What is the disaster recovery procedure? What is the recovery procedure? Normally, what I see, it's a mix of automation and human actions. If you're good, maybe you have a fully automated procedure, but I've never seen it. It's mostly a mix.
Well, and a lot of times in a disaster, those automated solutions are part of the reason why it became a disaster, because they didn't get triggered, right?
Right. Yeah. But that's the point. Somebody has to trigger them. They don't start autonomously. They're not always being continuously tested. And maybe when they start, they don't work well. We see, I think we have all seen all of these situations. In cloud native, we want it to be fully automated. So the system autonomously detects the problem and reacts to it. There is no human interventions. In this respect, a DR event is going to start looking as an HA event that we are more used to, right? So system keeps working and signals that there is a fault, but the service is still up. And then the two main metrics of disaster recovery are real recovery time objective, or RTO, which is essentially for how long the system is down, and recovery point objective, or RPO, which is what amount of data back in time do I lose because of the disaster, which is a measure of the consistency, right? And in traditional disaster recovery, the system can be down from minutes to hours. It could be hours if it takes a long time for me to react and do the recovery procedure. In cloud native, we want it to be near zero. So it can't really be zero, because there are some timeouts and some else checks that need to react to the situation and swing the traffic to the sites that are healthy. But beyond that, it should be really a matter of seconds. And as far as consistency and the recovery point objective, in traditional disaster recovery, you could have from 0 to hours, depending on how you organize your data sync or your backups and restores. But in cloud native, we want zero, exactly zero data loss. And then when we think about who is the owner of the disaster recovery procedure, formally the owner is always the application team, right? But what happens in traditional disaster recovery is the application teams stores the data in a storage system. So they turn around to the storage team and ask, what is your disaster recovery SLAs? And then whatever they answer, that's what they get. So essentially, disaster recovery is driven by the storage team. But in cloud native, it's going to be absolutely a responsibility of the application team to pick the correct middleware that can manage a disaster, and they own the responsibility. In part also because there isn't a storage team anymore, right? There is cloud storage, then maybe you have AWS or you have Google, and then maybe you have your internal on-prem storage, which perhaps in that case there is a storage team, but there isn't just a storage team controlling everything. And then another interesting insights for me, this really, it's a discovery that I did while I was creating this architecture, is that in traditional disaster recovery, the main capabilities for building your recovery procedure come from storage, and usually are the ability to do backup and restores, or the ability to do volume sync across sites. But in cloud native disaster recovery, we don't really need those capabilities. What we need is more capabilities from networking, more advanced networking. We need the ability to do east-west communication between the instances of our stateful applications that are geographically distributed. And we need a good global load balancer that can understand the disaster and move the traffic where we still have healthy instances.
So what's the effect for customers as they move towards this kind of more cloud native, fully autonomous DR strategy? You know, what kinds of decisions do they need to make to be successful in kind of implementing this vision?
Yeah, I think they have to pick a middleware product that can actually be installed in this fashion. There is a new generation of middleware products that have been built around the CAP theorem, which model availability in a situation of highly distributed workloads, and if the middleware is built, keep in mind this theorem, there is a chance that you can install it in a fashion that will essentially allow the middleware to automatically recognize a network partition or a failure and react to it. So I think that's the main requirement. And then the second is we need a highly automated platform to be able to do all of this automation, right? Almost, you know, it's more than automation. It's autonomous. It's autonomous decisioning from the system itself. And so I think systems like Kubernetes lend themselves to become the platform for this new generation.
Well, with that, why don't we take a look at some of the infrastructure that you built for this demonstration?
Right. So we have in this demo, we're going to have 3 OpenShift clusters in 3 different AWS regions. We could have built this with any cloud provider, but I just happen to have an AWS account that Redhat lets me use it for these demos. So 3 AWS regions, and I'm gonna tell you about some preparation work that we need to set up before we can actually deploy our stateful workload. On the bottom, you can see that there is this S logo. This is a component called Submariner, and it allows us to create a network tunnel between the OpenShift networks. In OpenShift, as you probably know, or Kubernetes, there is an internal network. Usually it's an SDN that the pods can use to communicate with each other. With Submariner, you can bridge these networks between different clusters, and so that they behave like a single larger network. So now our pods are able to communicate inter-cluster without having to do complicated egress and ingress, procedures. That way, when we are going to when we deploy our stateful workload, all of the instances can find each other and form a larger logical cluster. So that's the east-west that's how we solve east-west in this case. Like I said, it's a network capability that we need, and that's how we solve east-west in this particular instance. The other thing is at the top we have a global load balancer. In our case, it's Route 53 because we are in AWS. It could be a different product. It needs to be an intelligent load balancer though. A load balancer that at least has health check capability. So it's able to ping the different endpoint in the different clusters, understand what is up and what is down, and then reroute the traffic. That way, our client that connect from external to the cluster will be routed to LC instances. And then we have some administrative capabilities are on the top right. We have Redhat ACM, which is our product, our multi-cluster management product. And so it's the tool that I use to spawn these OpenShift clusters in different regions. And then we have a load balancer operator, which is observing the clusters and programs. Is able to program the global load balancer. So I don't have to go and manually configure Route 53. There is an operator that automatically does that. And then another piece of infrastructure that I built is that we have to establish trust between these clusters because other than that, otherwise they're just in clusters that don't know anything about each other at this point. So at the very minimum for CockroachDB, we needed to be able to have certificates signed all from the same PKI, right? All from the same certificate authority. And so I needed this cluster to source their certificates from somewhere, or the certificate that were going to be given to be supplied to CockroachDB from somewhere. And I decided to use Vault, which is the triangle here in this picture. And so I could have installed Vault anywhere, but I started to think about the fact that Vault is a critical piece of infrastructure, because without Vault, your stateful workload, and without certificates, your stateful workload doesn't run. So because we're building here, what we're building is the most available infrastructure that we're going to have in our data center, because we want zero downtime, even in the case of a disaster. Why it made sense to install Vault across this infrastructure, distributed across the OpenShift clusters of this infrastructure. So the 3 Vault logo that you see here, they're actually a single Vault logical cluster that is able to mint certificates for any workload running in these clusters, and all the certificates will be coming from the same PKI. Vault can be deployed with the Raft storage is a particular configuration, and Raft is the same underlying technology that also Cockroach uses for its distributed state sync. And I think Keith is going to talk more about that later. But essentially, Vault and Cockroach share similar technology to be able to be installed in this way. And that's, you remember before when I said you have to pick the right middleware. These are examples of middleware products that can be installed that way. And the final piece here, yeah, go ahead.
No, it's just go ahead, Raphael. I had a question. I'll lob it in at the end.
The final piece is an operator called Cert Manager, which essentially mediates the calls between the calls to provision new certificates that are then directed to Vault, and it makes it easier to provision certificates inside Kubernetes clusters. Go ahead.
Yeah. So, by the way, etcd also uses Raft, right? So there's lots of Raft going on in here. So one of the questions came in: is there any networking overhead bought by Submariner in comparison with what the host networking approach plus kind of an independent tunnel on an operating system would bring? So I guess what's the overhead of Submariner?
I'm not sure. Well, it's I need to understand what we are comparing it to. But let me tell you how Submariner works, and then maybe you can create your own opinion. Submariner establishes an IPsec tunnel. Okay, so it's an efficient tunnel because it's layer 3, inside a UDP envelope, but it's encrypted, so it's inherently secure, right? And what the Submariner operator does, it deploys a gateway, which could be an HA gateway, in some of the nodes of the cluster, and then so all the traffic that needs to cross between clusters has to flow through these gateway nodes. So you could say that there is a hub there in order to get your traffic to the gateway node.
So one of the challenges that we run into, because we've helped customers do this without solutions like Submariner in the past, and when you're not peering the container networks, when you're peering the host network, the discovery piece becomes very difficult to manage. You end up doing complex DNS chaining, and what ends up effectively happening is you're peering your container network to your host network, and then you're bonding your host networks, and then you have this complicated DNS chaining up and down the stack in all of these locations. It ends up introducing an enormous number of single points of failure, right? Mm-hmm. So if the Submariner gateway fails in one of these clusters, the effect is just like the entire cluster failed, but because the peering is being handled at the at the container network level as opposed to the host network level, when that cluster comes back online, the actual DNS, like the discovery and all that stuff, kind of just works itself out rather than having to then go in and then redo any DNS configuration and repropagate that information to cluster, which is a manual, painful operation. As far as kind of overhead, as Raphael mentioned, it's effectively it's a layer 3 or layer 2 over layer 3 or layer 3 over layer 2 technology. I was confused the terminology there. That's the same way you would do a VPN from your laptop to your corporate network, or between two corporate, like in a WAN and across two corporate sites. So the actual networking overhead is effectively the same. It's just we're peering the container networks directly rather than peering the host network and then having to peer the container network to the host network and then do all the discovery stuff. So it's a much cleaner solution.
Yeah. In terms of discovery, Submariner is compliant with a standard that comes from one of the SIGs. I think one of the SIGs that came after the one that you were mentioning before, SIG multi-cluster, one of the legacy of those SIG multi-cluster SIG. And so it's a very standard way of deploying this architecture. In theory, you could swap Submariner with something else that is compliant with the same discovery, and your workload wouldn't even know that. The other nice thing about Submariner is that this is an upstream project that will work with any CNI compliant SDNs. We are just operationalized for OpenShift, and I believe soon it's going to be GA'd.
Yeah, the other thing, because it follows that standard, it connects directly into the service discovery for the OpenShift clusters. So there was no like magic like config scripts or anything to make the discovery work across the clusters, and all the a lot of that stuff kind of came for free because we used a Kubernetes native network peering solution. Jim, it looked like there was another question from the field.
Yeah, no, there was just a quick follow-up. I mean, there was like, what's the state of Submariner today? Is it beta, alpha, GA? It was built by, I mean, it was built by I think the Rancher team originally built it, wasn't it, Raphael?
Yeah, initially it was from the Rancher team. I think they're still heavily involved. I believe there is some efforts for it to become a CNCF project, but I'm not sure what the state is there. For Red Hat, like I said, we are close to GA, so to provide full support for it. But I don't know the gentleman who's asking the question. If if he's talking about the upstream project, then I can't really speak to it.
So we only have 20 minutes left, and I want to make sure we get through the demo. So let's kind of talk about how we added CockroachDB on top of this as kind of our distributed state store. So we've already kind of talked about how Raft is kind of the underpinnings of all of the state that we're synchronizing between these clusters in a pretty real way. The nice thing about that is that installing CockroachDB across this infrastructure was, correct me if I'm wrong, Raphael, one of probably the easiest or close to the easiest thing that we had to do here, because we were designed for the ground up to do this. So we've got, in our scenario, we've got 3 CockroachDB pods running in each of these OpenShift clusters, and they're communicating across the Submariner network for us to synchronize state across all these nodes. And what we're going to be showing here today is we're going to run an industry standard benchmark called TPCC. It's been around since the 90s. So that, of course, means you can go and you can run it on probably every relational database that you could think of. We're going to run it with a client in each of these clusters, get kind of everything up and running, show that the state is synchronizing across all of these environments. And then we're going to simulate a disaster where we pull the rug out from under one of the clusters and remove it from the equation entirely. So we've got like 20 minutes left, so we probably should dump into the demo and then kind of come back for questions on how all this stuff works. Raphael, I know you've got the control and I've got the GUI. So here's the actual cluster running, right? We've got 3 nodes in US West 2. Correct me if I'm wrong, Raphael, this is the region we're going to take down, correct?
Yes, West region, yep.
Okay, so, and then we've got 3 nodes running in US East 1 and 3 nodes running in US East 2. So right now we don't have any queries running against this. Raphael, do you mind kind of kicking off those?
Yeah, I'm going to start some load on these clusters.
So you can see we already kind of preloaded the TPCC data into the database. So we've got, give this a second to start loading statistics.
Yeah, loading is coming through now.
So we already have data populated here. We're going to be running the TPCC benchmark. TPCC simulates a inventory management workload for n number of warehouses. So we're going to be simulating, I think, 100 warehouses today, which is a pretty small TPCC workload. I think, Jim, correct me if I'm wrong, I think we benchmark CockroachDB up to 140,000 warehouses. So this is intended more to kind of just demonstrate what happens when we simulate a failure. If anyone wants to talk about performance, we can do that as well.
Yeah, we're running TPCC every night, and actually the TPCC workload comes with Cockroach. It's a standard workload you just kind of run and by yourself if you wanted to. Right. Sorry for the commercial, but hey, it's there.
Hey, no problem. So we've got some queries running per second in each of these regions right now. So we can see that each of the nodes is getting, a dozen to a couple of dozen of queries per second. We'll give this about a minute to warm up. So one of the things that TPCC does is it warms the cluster. A lot of databases have query caching. And so there's a procedure for letting it warm up, and then it kind of starts firing away additional queries. So we'll give it 60 seconds or so. Once that triggers over to to more queries per second, we'll go ahead and rip the rug out from one of these regions. So you can see now it looks like West 2 is up to about 70 queries per second. If we were to go take a look at just kind of the overall query metrics, we're looking at, we're looking at some, a couple hundred queries per second right now, which is about right for the number of warehouses that we're going to be running. So Raphael, do you want to go ahead and remove a cluster, remove one of our OpenShift environments?
Yep, we'll do that. So what I'm about to do is to kill all the traffic within one of the VPC of the third cluster, the one that is on the West region. So it's effectively going to be completely isolated.
So, and this simulates a failure well, because not only does this infrastructure go away, but it stops responding. Effectively, all the traffic from US East 1 and US East 2, whether it's CockroachDB traffic or otherwise, goes into like a black hole. There's no response from any of those IP addresses, correct?
Yeah, that's correct, and that's why it's a perfect way of simulating a failure, because it's easy to react when somebody is telling you that it has a problem. It's much more difficult to react correctly when you lose the communication. You don't know if on the other side somebody has committed the transaction or not. There's just no answers.
So you can see go ahead, Jim.
I was going to say, you guys, this is like a backhoe went through the wire. This isn't the data center exploded, right? Like this is a pure connectivity, or is it just those nodes are gone?
So it simulates either of those scenarios. So a network black hole. So, a more graceful scenario would say, hey, this service is not available on this port, right? That's what might happen if we had a node failure, right? Mm-hmm. When you have like full connectivity blackout to a site, you don't know if it's a wire that got cut, or the power went out, or a fire, or whatever. It could be, there are a lot of things that can kind of happen there. You can see that CockroachDB detected that this was a problem. We're continued to run queries across the other two regions. So you can see that we're still running queries per second. If I go ahead and take a look at like our query metrics, I probably need to actually refresh, because I think the console version that I was on, I was connected to one of those nodes that went away. So the load balancer, when I refreshed, routed me to one of the nodes that was still healthy. You can see that we continued to run queries. We had a bit of a latency spike there for what that's like just a couple of seconds while we kind of sorted out what we needed to do. But our queries continue to run. We're almost back up to the same query per second load that we were before we lost those nodes. Things are still humming along, right? Our application's still up in 2 of the 3 regions. We're still responding to queries.
You just glossed over something as well, Keith, that basically the UI, the URL, you were hitting one of the nodes that was in the region that went out, correct? And then basically just pointed at any node in the cluster, you're going to have this UI across anything, right? Like actually, you really quickly went through that. I'm like, wait a second, it's kind of a big deal.
Well, and fundamentally, there's no single node, no single service, nothing in this demo is special, right? So every node in CockroachDB is a common gateway to the entire cluster, right? Yeah. Beyond that, though, right? We picked solutions for the entire infrastructure that allowed us that made those same kind of decisions. So if we wanted to go ahead and add nodes, and this isn't a part of the demo today, Raphael, we could still sign new certificates for those new nodes in the remaining 2 regions, because we still have 2 of our 3 regions available. So we can still, we still have consensus over, whether or not those two regions still have the availability or the authority to act.
Right.
So
if we went to the Vault console, we would be seeing something similar where also Vault is installed with 9 nodes, and we would see that 3 are down, but Vault as a service is still up.
Right.
And so that you can still create certificates. Yep.
So the entire stack from top to bottom stayed healthy, and that's what enabled us to do this. CockroachDB being, and a very important part of it because we're the state store. But Raphael, do you want to go ahead and allow West 2 to come back online?
Yep, will do. And one thing I like to notice is, as you can see, we kept working, but as humans, we didn't have to do anything. The system did everything by itself, and it's going to do the same when it recovers.
Right.
So no human intervention ever. Whether it's the disaster situation or the recovery situation, the system is always able to do it by itself.
Right.
So why you were alarmed? It's not the alarm in the middle of the night problem where everybody has to wake up and go fix something. It just basically resolved everything itself. It was funny, we were on with DoorDash, 2 weeks ago, right, Keith? And I think Sean was saying, it's not the bump in the middle of the night's the problem, it's the bump in the middle of the day. And to have these things just automatically resolve, they actually go find things like a week later, like they'll find issues that had happened, which is kind of interesting as well, because it all just gets resolved. So
yeah, absolutely. Well, and what's really important to remember when we're talking about these kinds of things, we made the developers actually responsible for being woken up in the middle of the night if their applications failed, rather than allowing them to have them page the storage team, right? Like Raphael was talking about earlier. And amazingly, all of a sudden, there weren't applications that are now being designed so people don't get woken up in the middle of the night.
Interesting.
So it looks like we're still waiting for those nodes to kind of come back to us. Were you able to kick that script off, Raphael?
Yeah.
Yeah. So one of the things that we noticed here in the meantime, the node was gone for more than 5 minutes from the cluster. So now they got tagged as dead. From that perspective, what that means is when they come back online, we may choose to bring them back into the cluster a different way. So a suspect node, we'll just catch it back up using the raft log. For dead nodes, we might make a different re-replication decision, and we might re-replicate the entire range depending on kind of the scope of the number of changes that happen to the data sets that are impacted. That's the only difference from a user experience there. So hopefully these nodes start responding to us here and bring back. Luckily, the database is still running. This is the great part about a live demo, right? Imagine you were in a scenario like this and like a third of your production infrastructure failed, right? And you didn't know why. Like, oh, here we go. It came back. Woohoo!
And by the way, every phone in this row is ringing right now, and 18 people are breathing down your neck, and it's a nightmare. What are you doing, Raphael? Come on, let's go.
Yeah, absolutely.
Right? But meanwhile, the database is still running, and P99 is still way down where we expected it.
It takes a minute because first the submariner has to reestablish all the connections, and then
that's right.
And then cockroach can start healing, right? But there was I'm trying to see what was happening because it took longer than the other times we run this demo. But
everything kept working anyway. So the only thing that someone might manually need to do, and that's just partially because we just didn't have this set up, because the client also failed in West 2, where we don't currently have any traffic going to West 2. We would need to restart the client. You could also set that up to auto heal. We kind of intentionally, that was fun. I think we reprogrammed the load balancer.
Yeah, it could be. I have lost. Let me see what's happening.
It looks like it's coming
There
back
we go.
right now.
Yeah, it works on my side. Yeah. Okay. Good.
The So anyhow, there we go.
So basically what you guys are saying, it's like everything healed itself, even with like little blips along the way. Traffic was never interrupted. Transactions were still being serviced. The only thing that didn't come back, Keith, was the TPCC client, the load creator,
Yeah.
right? That was the one piece, right?
Yeah.
And we just didn't design it in. So like, I get it. That's exactly what happened.
But in a real world, that is just to simulate a load in my demo, in my idea of the demo. But in real world, we would have customers all over, in this case, North America, opening connection to our service. So as West comes back up and the global load balancer realizes it, it starts redirecting some of the connection to West. So that's how you reestablish load also on West.
Yeah.
You don't have to restart anything manually.
That's right.
Well, and what's kind of amazing is even though we had problems with the demo, but the database kept humming along, even though we couldn't get to it for whatever reason. The database itself was still running and was still processing transactions and healed itself, which is, as anyone who's ever carried a pager knows, that's a huge, because nobody wants to get that call at 2 o'clock in the morning.
So Keith, there was one of the YouTube audience members was asking questions. How would it handle intermittent connectivity problems where the latency connection to a region still lives, but there is, say, massive packet loss or massive latencies between regions? I mean, is this a similar situation, right?
Yeah. So for a short period of time, we're going to be able to recover from that for sure, right? If you're permanently in that kind of a situation, we are a CP database. We're consistent and partition tolerant, so we can heal from those scenarios. We're not an AP database where we will respond to queries even if we can't guarantee the consistency. So the contract you have with CockroachDB is that we're a system of record, and that we guarantee that if we respond, that it's a consistent response based on the quorum of the nodes in the cluster, right?
That's right.
If availability is your number one priority, and you want to do, you want stale data, we do have some capabilities around time travel queries, which will give you a consistent view of the data as of, the latest available closed timestamp, for example.
Yeah.
For kind of certain specific read-only workloads. But as far as like actually being able to run transactions against the database and be able to insert data and do the work that you'd want to do, you would want to limit that periodic connectivity challenge as much as possible. We have been talking about things we could do in that area, but as far as the current state of the database, that's how it works today.
Yeah, cap is still cap. So guys, we have about 3 minutes left. Is there any final things you guys wanted to cover before we got into the reference material that you had, Keith? Or
no, Raphael wrote and I wrote a great series of blog posts on the OpenShift blog that covered exactly all of the stuff we did here. So there's a blog post on how we prepared the cluster, and which includes much more detail and all of the different pieces and how the load balancer gets configured and all of that stuff, as well as what we were able to do once we overlaid CockroachDB onto this architecture, right? So encourage everyone to go take a look at the OpenShift blog for more details on exactly how all of this stuff was built. And Raphael, thank you so much for joining us today.
It was a pleasure.
Yeah, I concur. Thanks, Raphael. It's really wonderful stuff. And it's like, this is real world stuff that we're dealing with all the time with customers. So it's great to see it in a demo. And actually, I love seeing problems in demos, you guys, especially when sorry, the database still kept working on the back end. We had problems, the database didn't. That's my quote of the day. So, but thank you, Keith, as well, for taking the time today. I mean, it's just, you guys, it's really, really killer stuff. And it's unique in that we're able to accomplish this, but it's not a unique challenge. I think is something that's going on out there all over the place. So there are some really, really great articles that these guys wrote that we'll make sure to get this into the feedback in the follow-up email and whatnot. But my last request is for everybody in the audience, thank you for joining us as well. But please do, there's a survey at the end of this session that we take very seriously. We do like to get better every single time. We have our own objectives and metrics that we have to hit in terms of audience satisfaction. So please do fill out the survey. It is important to us. But Keith and Raphael, thank you guys again. We're gonna do something similar to this, I think, in a couple of weeks with the Linux Foundation, aren't we, Keith? And on a webinar on the Linux Foundation, aren't we?
Yeah, it may or may not be quite as production grade as this was, though. Raphael
might be more funny.
Really went the extra mile to make sure that if a customer went and tried to do this, that they would be set up for success. So this is by far my favorite demo to show customers that really care about solving this problem.
Yeah, by far and away, just the layers and layers of redundancy and survivability, Raphael. Thank you so much.
You're welcome.
All right. And thanks everybody for joining us. That's a wrap, guys. And everybody have a great day.
Thanks.